Okay, so for 12-1 tangent lines, we're talking about tangent to a circle, so not to be confused with tangent when we're talking about trigonometry and right triangles. It does relate, but we're talking about tangent to a circle. So it's a line that touches a circle at one point. So we'll have a circle and a line, and it touches it at one point. So it doesn't touch it at multiple points. It doesn't like go through the circle. It just touches it at one point. So like it just barely touches the circle. Tangent. Okay? If a line, so there's two theorems that go along with tangent to a circle. The first one is if a line is tangent to a circle, that it is perpendicular, aka forms a right angle, to the radius drawn at the point of tangency. Okay, so this can form a right triangle, as you guys can see here. So what that means is I have a radius right here, or a diameter, doesn't really matter, because both of those go through the center. The point is that the tangent line is perpendicular to the line that goes through the center. It forms a right angle, which means this is a right triangle, and we can use the Pythagorean theorem here. So our if statement is if AB is tangent to circle O at point P, then OP and AB are perpendicular. Okay, this works backwards too. If these are perpendicular, then this must be tangent. Okay, so remember tangent, it touches the circle at one point, so that's point P. And for the most part, problems will state lines that appear to be tangent are tangent. So it's important to keep that in mind. Okay, the other one is if two segments from the same exterior point are tangent to the circle, then they are congruent. So we have this point, and then these two lines are tangent. And what we end up using this to solve problems with are usually either perimeter problems, so it'll have an inscribed circle and a triangle, and we'll know that both these parts are the same, both these parts are the same, and both of these parts are the same. We can add them all up. The other type of problem it would have is we might have two radii here, so radiuses, and then it'll form a kite. So we'll know both of these angles are 90 because of this theorem up here. And then it'll give you one of these two, and I'll ask you to find the other one. Okay, so let me show you an example of that. So right here, let me zoom in. It's asking what's the measure of angle x. Well, I know because ML and MN are tangent that these angles are 90 degrees. And I know 1, 2, 3, 4-sided shapes equal 360. So I can say 90 plus 90 plus 117 plus x equals 360. Add it together, I get 297. Subtract that from 360. X is 63 degrees. Okay, so let's look at another example. Now, this example is really important. So we have radius, and the radius is always going to be the same. So the radius here is going to be the same as the radius here. Okay, so we got to take in mind that the hypotenuse, always a side across from the right angle. Remember, the tangent and the radius forms a right angle. So hypotenuse, we have to add up the radius plus this extra part. Okay, radius plus this extra part. So then we can do a squared plus x squared equals this c squared, as we can see here. And then, sorry, I'm trying to let you see it. And we can get what TE equals approximately. Most of these problems you don't leave in simplest radical form. You want to round them to the nearest thing. This is another very important problem, and this relates to distributing binomials. So we still have a squared, so x squared plus 12 squared, but then our hypotenuse is a little bit different. It says x plus 8 right there. Okay, that's x and that's 8. So the whole hypotenuse is not 8. It's x plus 8. So we have to say the hypotenuse is x plus 8 squared. And remember, when we square that, it's not just x squared 64. This is the same as doing x plus 8 times x plus 8, where we have to distribute x times x is x squared, x times 8 is 8x, 8x plus 64. So that's where we get the 16 in here, okay? Is when we combine those two to be 16x. Oh, not equals, plus. So now when we go to solve this, the x squares actually end up canceling each other out. So when I subtract x squared, that'll go away, and then I'm just left with this. Subtract 64, I get 80. Divide by 16, I get x equals 5. And so that's really important there as well. Okay, if you recall, we can know if something's a right triangle if a squared plus b squared equals c squared. So we can check it, and if it equals, then that must be a right angle. And if that's a right angle, well, then this line must be tangent. Okay? Last example, I think, right here, it says that it doesn't say anything about tangents. Oh, it's inscribed. So that tells you that the tangent, these are each tangent, okay? These each touch at one point. And our second theorem stated that if these touch at one point, well, then these are both the same. So if this is 10, this is 10. So 10, 20, 8 plus 8, that's 16. So 36 plus another 30, 15, and 15. So we get 66 down here. So that's how we can add up all the different parts. Now, if it gave us that this whole part was 18, and it didn't give us this 10, we could do, well, 18 minus 8, that must be 10, so that must be 10. So you can use those tricks all the way around the circle. Let me double check. There's not another example. Nope. So that is what 12-1 tangent to a circle is all about.